We're waiting for
People are slowly moving more towards the back of the room. What's going on? Like the journals are really interesting. You're reading the annals of brain and brain pathology. Brain pathology would be particularly good.
Latent force models in brain biology.
I recommend. I might even have a paper in one of those. Okay. So I think we've heard. I thought that was a really good talk by Timo that sort of described how the overlaps between the some things myself and Mauricio talked about this morning, and what goes on in signal processing. He's really reached back into sort of reading back to Stratanovich to sort of understand all these things, and it was, I thought, a really great privilege to hear from him. So I think what Mauricio is going to talk about now is a couple of extensions to the latent force model framework you heard about this morning, and then I think he's also going to try and do some work to put these methods into some kind of context. We've heard the signal processing context to some extent, but in a wider statistical context, and also machine learning as well, but mainly statistical.
Yeah.
So over to Mauricio.
Okay, thank you. Okay, so we'll continue with the talk of this morning. I'm going to talk about some extensions of the linear latent force model we saw this morning. One of them, it's a really extensive work we did, but the others were done by Antti, I think, and Michalis Stitsias, postdocs. So I'm going to mention only those ones. These are two of them. So you can do nonlinear latent force models if the likelihood function is not Gaussian or the differential equation is nonlinear. You have to use some kind of approximation. And so in the original paper where all this started, Neil used the Laplace approximation, and then Michalis Stitsias, who was a postdoc at Manchester, was doing a lot of sampling on those nonlinear latent force models. And this is another extension, cascaded latent force models, where basically the latent force models we had before this Gaussian process could be the outputs of another latent force model. So you have a series of latent force models. Particularly, Antti used this for gene expression data. Yeah. So now I'm going to talk about more extensive work on switch latent force models. So let us remember what is a latent force model then. So the idea in a latent force model is to encode the interaction between multiple related dynamical systems in the form of a covariance function. So you want a covariance function to express the correlations between several dynamical systems. Remember that each variable is represented as the output of a differential equation, a linear differential equation. And those differential equations are all driven by the same sum of weighted latent functions. That's basically what a latent force model is. So we assume that those latent force models or those latent functions all have like RBF covariance functions or things like that. They are usually, we assume that they are very smooth functions. But now we are going to move to discontinuous latent force models, where you will allow these latent functions to be basically discontinuous. Yeah. So why discontinuous? Because discontinuous latent functions have a particular meaning in practical applications. So think about impact forces due to contacts in mechanical systems, for example, or switches in an electrical circuit. The real-world data examples that I will show are basically are related to humanoid robotics, what we want to do is to find something that they call the motor primitives. So I don't know if somebody is anybody familiar with these motor primitives? So the idea is that you want to teach a robot basically to reproduce the human movements. Yeah, that's basically humanoid robotics. So there is a theory in this field that says that you can construct very complex movements using like some combination of very simplistic movements. Something similar to what you do with language, yeah. So you have basic units, and then you combine those units, and then you can make more complex sentences and text. So if you can find which are the motor primitives, then you can combine those motor primitives in a clever way, and then construct very complex movement, and then you can teach that to a robot, and maybe it can reproduce those movements. Yeah. So the application we are studying is, if I give you a multivariate time series, can you find in that multivariate time series those motor primitives? Can you segment them in first place, and then maybe you can cluster and find some meaning? But we want to find to segment them first. Yeah. Okay. So let's go back to the basic latent force model. I'm assuming one output. So you have your spring, your damper, you have your mass, you have your force, and then some sensitivity of the force over the system, and you are measuring the output. And remember that the force, you assume that follows a GP with a covariance function K. So this is maybe a sample from the latent force, and then this is something that you get in the output. So for our switch latent force model, we will assume that these parameters, spring, damper, and mass and sensitivity, can change as a function of time. So what we will have is a latent force with a covariance function that is actually changing according to the input space, which in this case time. So the idea is something like this. So there is a time interval in which you have a latent force model. There is another one with a different latent force, and there is a third one with a different latent force. Then each of those generate outputs. So this is your output in interval 1, your output in interval 2, and your output in interval 3. And what you really observe is this, yeah? So you really have, this is what you get, this is your data. What you want to find is these sort of forces, yeah, which are discontinuous. That's the objective. So there is something important here. I think, Mike, you have a paper on, okay, so what you were talking about before, change points. So there are so many ways you can analyze these change points, because you can do it in the input space, or in the in the input, yeah, in the input or in the output, yeah. So here we are interested in a particular important restriction for the outputs, and is that the outputs have to be continuous, yeah, because this is a robot application. So we don't want the outputs to jump. We want the outputs to be continuous. So that's going to be an important restriction for constructing the covariance. Is that okay? Right. So this is the way in which we are going to do it. So assume you have these intervals, and for each interval you have a basic latent force model, the ones that we explained before. So in the latent force model I explained before, we didn't take into account the initial conditions when we solved the differential equation. So we basically said those initial conditions were 0, but since we want the output to be continuous, and we are assuming that for each interval you have a different latent force model, you have to take into account now those initial conditions. So basically that's the trick we are going to use. When I use a latent force model for this interval, I have to take into account that if I'm using a second order differential equation, the initial condition in the position here and the initial condition in the velocity here should be, or should have the same value that the values of the output position in the last interval and the velocity in the last interval. Is that clear? So that's a way to assure the continuity in the output. So before, we didn't have this term and we didn't have this term because we assumed basically that this initial condition in the position and this one in the velocity were 0. So we only have this, yeah. So this one was this integral. You maybe remember this Green's function, and then you have the latent function. But now we have this initial condition on the velocity, and we have these functions. I didn't put the equations here, but these functions are deterministic. Yeah, so a combination of exponentials and cosines and sines. Okay, so once you realize this, the thing is that you want to compute the covariance function between an output D and an output D prime, for example, Z D prime. So you have to take into account the correlations between, So let's say you have, this is one of your outputs, and this is the other output. For simplicity, we have only two. So what I'm saying is that, say, these are your intervals. So this is T0. Yeah, so you're assuming that you have a latent force that is acting here, maybe something like this. You have another latent force acting here, another latent force acting here. So when you compute the covariance between this output and this output, let's say in this third interval, you have to take into account that these initial conditions here will depend on the action of the latent force model here. Yeah, because this latent force model, this latent force somehow was responsible in generating those initial conditions at some point. Is that clear? Yeah.
So those points have to be known a priori.
Yeah, that's true. Well, no, you can. I mean, what we do in this framework is that we optimize them. I mean, we find them by optimizing the marginal likelihood.
It's similar in that sense to what Mike was doing. That your model's conditioned on some point, and what Simo had said is, well, you could put an HMM. So you could put a prior over those things, but at the moment you've got a model that is conditioned. The covariance function is dependent. The final covariance function is dependent on the switching points.
Yeah.
In the same way that Mike's covariance function would be dependent on the switching points.
But then you optimize rather than marginalize.
Yeah, I mean, we could marginalize. Well, I'll let Mauricio.
Yeah. Yeah, we could do a lot of things, different things. But now this is like, we were interested really in the covariance. And, okay, so it's clear that the covariance here will depend on what was the value of the latent force here. Is that correct? So what is the problem? Well, so the problem with this is that you get a very huge covariance function because it would all depends on how many intervals you have. So every time you put a new interval, your covariance function is growing. Yeah. Okay.
But the changing point, the time point is unknown, right? You don't know the time point.
No, you don't know. You don't know. No, you don't know where is the time point. Yeah. Okay. So this is a covariance function of that sort of we constructed. So you have three intervals, and the important thing in this covariance is that it is continuous. Yeah. You see, it's a continuous function. And these are samples drawn from that covariance. In the outputs, I don't have here the latent forces, but in the outputs, so you see like there was a latent force acting here, the first interval, then a new latent force appear, and the outputs start reacting, thanks to that latent force. And then here again, you have a latent force acting and sort of makes the outputs move again. Okay. So these are toy examples. So we took some parameters for that covariance function, and we obtained some samples, and then we used those samples for training this latent force model with switches. And so here we have the predictions for these two different settings. So here you see that the latent force is quite discontinuous, yeah, and you get these outputs. And in this one, so you try to have one latent force here, which has a big length scale. This is short length scale. So here the length scales are different, and you get that effect on the outputs. It's a different example. Any question?
So the output 1 on the toy example 2, it doesn't respond to the slowly varying. So is it under? It doesn't respond to the slowly varying input, but it responds. I can't remember this. It responds to the rapidly varying. So do you remember what its parameters were?
No.
Whereas output 2 responds to the slowly varying. It's quite nice that, I think.
Yeah. This one is following. What you mean is that this one is not following the input?
The output 1 toy example 2 doesn't follow the input initially, but then follows it very closely.
Okay.
And then output 2 toy example 2 does respond to the initial input, but then I can't remember why that was. So if you remember. No.
It could be a resistor burning down. You increase the current at a certain point, it breaks up, and then it starts varying rapidly, the junction breaking up.
Yeah, no, Michael, but this is samples from the model, so I can't remember why it does that. So this is known. It must be the way that the latent force model for output 1 is parameterized that it can do that. Because it's quite a nice effect, I think. But I was just trying to think what the explanation for why it does it is.
I think it's related to the parameters of that.
Of that dynamical system.
The dynamical system.
If it's being pushed slowly and it doesn't respond, but if it's being pushed rapidly, it resonates or something.
Yeah.
Yeah, it would make sense.
Okay, and here is an example with the real data. So this was an experiment we did in Max Planck, working with Jan Peters and Bernard Sholkov. So as I said before, the task is to segment discrete movements that are related to motor primitives. Yeah. So we did this data collection work. We had a human to take a robot and teach the robot some movements, table tennis movements. This is a robot of 7 degrees of freedom. Then we took those outputs, which are basically angles, as in the motion capture data. Okay, so we did several tries using different data sets, actually. So different segments. These were, we were recording like for 2 hours, and we were just segmenting, finding in those 2 hours some segments to work with, and these are 2 different tries we did. So we don't know how many switches are in the data. So what we did was a very simple thing with the marginal likelihood to see how many segments you could find in the data. So this is the form of the latent force with different switches, 9. And this is one of the outputs of the 7 outputs in that try. And then in a second try, we sort of got the same number of switches. So this is a different output in the robot example. So this is like a first step, yeah, to being able to, given a multivariate time series, being able to segment the different motor primitives. Yeah, and then people in robotics find that very useful because then they can cluster those time series, those motor primitives, and see if they can teach something useful to the robot. Is there any question? Okay. Okay, so now I'm going to talk about some related work to latent force models. So you can see this from very different perspectives. I'm just talking, I will talk about three different perspectives you could look at these models. So the first one is that you can see them as multiple output Gaussian processes. That's one way of saying this, with a very particular covariance function. The other way to see them is a way to estimate parameters in differential equations. Yeah, because when you do the maximization of the log marginal likelihood, you are basically finding point estimates of your parameters that you have in your differential equation. Sometimes those parameters could be important. Yeah, for example, in computational biology applications, they have some physical meaning that is important. Sometimes they don't have that meaning, but maybe that's something useful. And then I'm also going to talk about Gaussian process for systems identification, which is related to this. Okay, so this is something that Neil gave a talk about this week, Gaussian process for multiple outputs. So this has been studied a lot in the geostatistics literature, the spatial analysis literature. So there are books about this. We have a paper in which we sort of make a general model, and then we show how many different models in the machine learning and the geostatistic literatures are sort of particular cases of that model. So this is the problem that we want to solve, is to find a covariance function. Let's say you have this output, so you can use a particular kernel function for your Gaussian process, and then you have your kernel matrix, but then you have not only one output, you have several outputs. Yeah, you can have kernels for each of the outputs. But then what you really want to do is to find cross covariances. Yeah, you want to find ways to make those cross covariances meaningful. So we sort of propose this form for the general covariance of multi-output Gaussian process. So assume you have d outputs, and the covariance between ft and ft prime follows this form. Yeah. So you have this double sum over Q, and then you have this other sum over I. You have these Green's functions, and then you have your covariance of your latent functions. And something that you have to notice here. So this Q refers to the covariance of the latent functions, but you're forming clusters of latent functions and allowing those clusters to have the same covariance function, but you can sample from each of those covariance of these Gaussian processes independently. So that's why you get this other sum that you have here. Yeah. So that's like a very general way, and then we can describe very particular cases of multi-output covariances using that form. So for example, in the linear model of co-regionalization, we assume that these Green's functions are delta functions of this way. So a constant ADQI, and then we end up with this covariance function. Yeah. So that's one particular case of this general framework.
Isn't this the green function that Simon talked about before? This GD, since when I look at this equation, we call that.
Yeah, so these GDQI are Green's functions, yeah. Yeah. So but you can do very simple models out of this one. Like, for example, saying that this G is a delta function this way. Yeah. So if that happens, then you get this model here. So in some sense, this is a dynamical, this could be a dynamical covariance function, yeah, because you can include dynamics in these functions or relate them to differential equations, for example. But here, what you see in the latent functions immediately propagates to the outputs, because it's like instantaneous combination of these latent functions.
What we talked about earlier, the case where the covariance function was a delta function, i.e. the white noise process, which also allows you to move, well, it makes the double integral over the Green's functions simpler in many cases. So this is almost like, this is an alternative simplification, but it just maps back to the case where there's no convolution, in effect.
Yeah. Okay, so you could also do the semi-parametric latent factor model. So basically you have the same assumption for the Green's function or the kernel smoothing function, but now you reduce the number of terms of the sum, so it's just one term in the sum, and you get this model. So basically you can have the covariance for the outputs is going to be of rank 1 basically, and then you can have different latent functions with different length scales. So that's the semi-parametric latent factor model. You could also have the intrinsic co-regionalization model, or what they call the multitask Gaussian process. So again, you have that form for the smoothing kernel, and then now the difference is that is this sum the one that has one term. Yeah, the other sum stays general. So you get this sort of thing. So now you have only one latent function. You have one latent function, but you allow the covariance between the outputs to be ranked U1. Yeah. Is that okay? Any question?
So for the green function here, is that a property of green function, or is it just an assumption for the relationship between the green function and the delta function?
Yeah, it's just an assumption in order to get these other models. Yeah.
Just thinking it's actually, it must be the Green's function of a system with no mass or damper.
Could be.
In effect, because it's the instantaneous response to a delta function input is a delta function, right? That's what it's saying. It's where there's no, it's the instantaneous system. Yeah.
Okay. So there are people have studied modifications and extensions of this basic framework. So again, we have this equation, and so you can think about a lot of different covariances for the latent forces. So we made emphasis on RBF covariances, and but people have tried, for example, OU covariances for KQZZ, Brownian motion covariance, just to name a few. So another thing people have done is the non-stationarity. So you can make this non-stationarity either through this function or through the covariance. So either through the smoothing kernel or through the covariance of the latent functions. What you do is that you allow the parameters of either the smoothing kernel or the covariance to change according to the input space. So in effect, that's what we did for the switch latent force model. Yeah, because we allowed both things to change according to the input space. Yeah. Okay. So people also talk about discrete convolutions. So this is the idea in which you don't use the integral, you use a discrete convolution. Then you can also put a Gaussian process prior on the latent function. And these are some applications people have used these models for. Okay, that's one way of seeing these latent force models, like multi-output Gaussian process. Is that clear? So now we're going to talk about parameter estimation and differential equations. So the idea is that, as I said before, one way in which you do hyperparameter learning is that you optimize your log marginal likelihood. Okay? So you get point estimates of your parameters of your differential equation. So I think this hasn't been explored that much in statistics and machine learning. Maybe there is a field called functional data analysis in which people have worked on. So let's say you have some data and you have some differential equations. How do you fit the parameters of those differential equations to data? Yeah, that's the point. So as I said before, given a differential equation without known with unknown coefficients, how do we use data to fit those parameters? And some classical approaches to fitting those parameters are numerical approximations of initial value problems and collocation methods, just to name a few. So in these two references, you can find some other methods to do that. Yeah. So let's talk about the numerical approximations. So basically, it is based on iterative process. You start with initial set of hyperparameters theta 0 and some set of initial conditions, and then what you do is you use a numerical method to solve the differential equation. Yeah. And the parameters of the differential equation are optimized by minimizing an error criterion between the approximated solution and the observed data. So you use like some sort of least squares, for example, between the actual solution of the differential equation that you find using numerical methods and the data that you have, and you find the derivatives of that error function with respect to the hyperparameters. This is the parameters of your differential equation, and you make the iterative process. Yeah, that's one way people use to solve that problem. The other thing you can do is use collocation methods. So you assume that your output function could be written as a linear function, linear combination of basis functions that we have here. Yeah. So the important thing there is that the basis functions must be sufficiently smooth so you can get derivatives over those things. Yeah. So you also use an iterative process for fitting the additional parameters involved in the differential equation. See? A particular case of a collocation method is principal differential analysis, in which the basis functions are splines. Yeah, so you can get derivatives of the splines, and then you use data that you have for the outputs and data that you have for the derivatives, and then you do some sort of principal component analysis, but in this case it's called principal differential analysis, to find the parameters of your model. Okay, so that's those are two very classic methods, and this is another method of this collocation method that use Gaussian processes. So the point there is that you can find, or you can propose an approximated solution to the differential equation that you can write in this way, where this kernel function is fine by making the derivatives with respect to the input space as many times as the order of your differential equation. And then so that's the way you can find the solution to your differential equation, and then you can use the same things that you use in Gaussian processes to optimize to find the parameters. Okay. Is there any question? Okay, and the third view about the latent force models is this Gaussian process for systems identification, which is something that is really useful in control engineering. So systems identification refers to a set of techniques that you use for representing dynamical system by a mathematical model. Yeah, so usually when you don't have any idea of how your data behave, you just basically use a linear model, for example. Yeah, and then you use that as your physical model, as a representation, a surrogate of your physical model. So people have used Gaussian processes for systems identification in the past. There are some references there. So one simple way is that you could express your function as a Taylor series expansion, for example. And then you can assume that these terms are your covariates, and the derivatives are the regression coefficients. Yeah. And then you can do, for example, Bayesian linear regression over that. Or there is this other view of state-space models. So, for example, when you don't know which is the connection between the latent space and your observation space, you can put Gaussian process priors over that. There are some references there. And this other view that we saw in detail with CIMO, where you assume that your latent process is EGP, but you express it as a state space model. Okay, I think that's all. Yeah?
In the approach for system identification, are you trying, for instance, to find, when you write your dynamical system equation, like the A matrix or something like that, the parameters of the system? So I'm wondering, in these approaches, are they imposing certain, like, you may have a system, you have to have it being controllable, for instance?
No, they don't talk about that. No. Just talk about just to have a surrogate model, so you can work with that to do the control phase.
But then, where does the word identification comes from?
Yeah,
What do they identify?
The system.
which is represented by your matrix, for instance,
Yeah.
system matrix.
Yeah, I mean it's related to this idea. I mean they use a lot linear models. So you assume, for example, autoregressive process, yeah, and then what they try to do is to find those coefficients in the autoregression process, and so they identify the coefficients. Yeah.
So I was wondering how, in the systems identification framework, how exogenous inputs are treated, as in controlled inputs as well as autoregressive ones. So like, one thing you can do in systems identification is try and fit an ARX model. So you've got terms being driven by noise, and then also from your own feedback. How is feedback treated in this form?
I haven't seen that. Yeah.
I think Carl Isaacson and Roger Frigola have a paper on, I guess, NARCs, which is the Steve Billings thing from Sheffield. I haven't looked at this stuff in detail, but I think this is all quite easy. I mean, the exogenous, I think, is quite trivial to include.
Okay.
I mean, I don't know. It's just like another input. You just have to put it in the right place. Making it nonlinear then has all the nonlinear issues that we've got different techniques for looking at. But I don't think it's a sort of quite understood why they. But maybe I just didn't understand it. Why they make a big deal out of adding exogenous inputs to an AR model. I mean, is it difficult? I'm not sure. I don't know.
Well, I just wondered about if you can learn because you know what you're putting in there. Then, and if you start getting wild predictions that are completely wrong, then you know your surrogate is wrong, basically.
Yeah.
But they do that for control applications, yeah, because if you can you can manage your input, you can make the system to go to places where you want to. Yeah.
But I don't know. Is there any reason why it'd be difficult to incorporate?
I think it depends on the form you assume for your state space model. Because I think, for example, Mark Deinsenroth is doing control with this. But he uses these nonlinear transformations of the input space to the output space. So the approximations there are quite nasty.
If you have closed loop, then what happens is that your control signal is correlated to your noise. So then it becomes more difficult.
Okay.
But it's still possible to do that.
Yeah. Max?
This question might be trivial, probably it is, because I don't know green functions, but in the multi-output GP, latent, latent force models, can you include prior knowledge into your cross covariances?
Yeah, I think that's that's one of the important ideas in latent force models. Yeah, that you are including the knowledge that you have about the system in these Green's functions, because those Green's functions you can derive them from the differential equations.
Okay, yeah.
Yeah.
Another thought Mauricio had and I had a long time ago was actually to fit the Green's functions. So come up with maybe a parametric form for the Green's function, and so learn the impulse response of the system. And I think that's very related to, have you seen this Andrew Wilson's work where he's actually learning the spectral density, which is another way of, so what we wanted to do was learn these Green's functions because we sort of thought that has a physical meaning, and actually, I don't know, people try and reverse do simple identification by trying to understand the impulse response. So that was one thought we had but never had time to pursue, and I think that Andrew Wilson idea of these very flexible covariances by learning a spectral filter is similar, but actually there'd be less constraints on the Green's functions, right? You could learn various non-parametric forms or something. The questions. Everyone tired. Yeah, 4 long days. Okay, well, if there's no other questions, can we just thank Mauricio?
Thank you.
So I think we could do a further discussion, but we did one before Mauricio's talk with Simo, I guess. And I guess people also have trains and stuff. Catch feedback. Yeah. So we could do a feedback session. Although I think what Nicolas is going to create, I sent out a link to a SurveyMonkey site, and it would be great if you could fill that in. I guess not so much for the late